Welcome to the 9th webinar in the RUS series. This time we will have a look at simple ways how to detect active fires using Sentinel-3 SLSDR data. And I will also explain a bit on how a RUS service can help you when working with Sentinel data. So my name is Teresa Šmejkalová and I will be guiding you through this webinar today. And don't worry if you miss some parts of the webinar is going to be recorded or is being recorded. And you will be able to repeat the exercise by yourself and replay the webinar as many times as you like. If you should have any questions during the webinar, please write them directly immediately when you have them, because in the end we will only have 30 minutes for Q&A session. So in order to answer the majority of your questions and not leave any questions unanswered, we would ask you to pose them directly. Okay, so first few words to the organization. So this webinar will last approximately 1.5 hours. 1 hour from that is going to be the technical part or introduction and the exercise, plus then we will have in the end up to 30 minutes for questions. So first I will introduce a little bit about RUS Copernicus. You might already know it, but I will just do a quick introduction. After that I will tell you a little bit about the study area we will be looking at today, and afterwards also a little bit about Sentinel-3 and the SLSDR sensor, and after that we will start with the exercise and the Q&A session. So first about RUS service. So what is RUS Copernicus? It stands for Research and User Support for Sentinel Core Products. And it is an initiative funded by the European Commission and managed by ESA, with the objective to promote the uptake of Copernicus Sentinel data and support R&D activities. So it is free and open scalable platform that offers a powerful computing environment in the form of virtual machines that are pre-installed with number of open source toolboxes such as Snap, including Sentinel-1, 2, and 3 toolboxes, QGIS, BRAT, Orfeo toolbox, and many others that you might be familiar with, and also with development environments such as R, Python, and others. So in this case it's ready to use. You can also install your own software or software that you have appropriate licenses for. And apart from that, we also offer a specialized remote sensing help desk that can answer any questions that you might have regarding the processing of remote sensing data and any technical questions regarding to that. We also offer training activities such as this webinar, for example, and face-to-face events at various conferences or standalone. So our next event, for example, is Urban Mapping Workshop at the URSEL Urban Mapping Workshop in Bochum next week, but we have many others and you can always find them on the web page where you have registered also for this webinar. I will show it again later. So talking about the web pages, so these are the two web pages that you might be familiar with already. First I will show you the RUS training web page that you've already seen when you registered for this webinar. So on this web page you can find all our future and past webinars and trainings. So if I go to the past, you can see our face-to-face and webinars already present here, and if you go to the webinars you can also find the recording. So for example, our last webinar was on land subsidence mapping with Sentinel-1. And if I now go to the webinar, I can find a video of the full webinar, excluding the question and answer session. And you can also find a summary of the question and answer session here in the Q&A PDF document. You can see also our upcoming trainings that I've mentioned already. So at the moment we have 2 face-to-face events here, but soon there should be some more webinars announced as we try to do a webinar every month. And the next part of the web page is also the e-learning page, where we at the moment have 8 lessons on the principles of radar remote sensing. So if you are interested in that, you can have a look here at the lectures. Okay, so that's all for the RUS training webpage. And then if you wish to repeat this webinar, I will now show you the RUS Copernicus portal. So this is the portal web page where you can request a virtual machine and access a virtual machine. So just first to say a few words, if you want to know more about RUS, you can go here and see what it is, who is behind it, and so on. Here you can also see what we offer in terms of the computing environments. So there is the list, a full list of available software. But as I said, you can also add your own software. And here is the overview of the limitations or ITC resources. So we generally divide our users into 3 levels based on their requests or their requirements in terms of processing power, disk space, and duration of the virtual machine. So this generally depends on description of the project or processing that you wish to do on the virtual machine. So now to move to how to request the virtual machine. So there is a video available on our YouTube channel, which I'll show you in a little bit, that details exactly how to register for the Copernicus SSO account in order to be able to access the RUS Copernicus portal and in order to be also able to request a virtual machine. But once you register for the RUS portal, you can just sort of simply log in. And once you log in, you see this new tab that's called your RUS service, where you can edit your profile, see your training, and also go to your dashboard, which is the most important part for us today. And here is the list of the virtual machines that you have assigned. So at the moment, I have one virtual machine that I will be doing this webinar on, or I will be using to do this webinar. However, if you are a new user, you will probably not have any, so you can request the user service using this button. I will not again go through the request. It's quite simple, but it's in detail explained in another video that we have available on the YouTube channel. So now I will go back to the presentation. Also from this page, just so I forgot to add, there is you can access your virtual machine once it's assigned to you, and I will use this in a second to start with the exercise. Okay. So as I was mentioning a couple times, we have a YouTube channel where all the webinars are also available, so all the recordings are also available, plus some additional videos on how to download Sentinel data, how to request a RUS virtual machine, and how to register to RUS Copernicus. Okay, so now a few words about our study area. So you might have heard that in June 2017, a series of deadly wildfires erupted across central Portugal within minutes of each other, and they were all following intense heat wave that saw many areas of Portugal exceeding 40 degrees Celsius. During the night of 17 to 18 June, there was additional 156 fires that erupted across the country, particularly in a mountainous region about 200 kilometers northeast of Lisbon. And while this was not the only event during the 2017 in Portugal, during the year up to 520,000 hectares of forest has been burned in Portugal, which is 52 times the size of Lisbon and represents nearly 60% of the total area burned in the entire European Union in 2017. It is also the highest amount of land burned in Portugal, ever in Portugal's history. So this gives us a good reason why we need to be able to detect the active fires in remote areas as soon as possible, and satellites are giving us a very good tool to do this. So how can we actually achieve this? So we can use the tool or the sensor available on Sentinel-3. It's called SLSTR. And SLSTR stands for the Sea and Land Temperature Radiometer, and it is a dual scan temperature radiometer in low Earth orbit, so approximately between 800 and 830 kilometers of altitude, as I said, on board of Sentinel-3 satellite, and it employs a long track scanning dual view technique for 9 channels. What I mean by dual view, so you could see this on the video, but it means that it's looking at the ground from a nadir view, but also from oblique view, looking backwards. And it has, as I mentioned, 9 channels. So it has 3 channels in visible and near infrared part of the spectrum. So then another 3 channels in the shortwave infrared part of the spectrum. Those are the radiance bands at 500 meters resolution. So 1 to 6 have 500 meters resolution, and they are radiance or solar reflectance bands. And then there's another 3 bands, 7 to 9, which are the thermal infrared bands at 1 kilometer resolution, measured or given in brightness as brightness temperatures. We also have 2 dedicated fire bands called F1 and F2. And they are dedicated to high temperature event monitoring at 1 kilometer resolution again. And they do this, or they are available like this because they have extended dynamic range. So they are at the same wavelengths as bands 7 and 8. However, due to the fact that they have the extended dynamic range, they are able to measure or detect fires at up to 650 Kelvin without saturation. Therefore, we can use them to detect sub-pixel active fire events. The Sentinel-3 or SLSDR products are distributed as level 1B or level 2 products based on the type and level of preprocessing applied to the raw data. So not all of the products are available to public. In this training, we will be using the level 1B RBT product, which consists of the full resolution geolocated radiometric measurements for each view, meaning nadir and oblique, and for each channel. In this training, we will only be using the nadir view of the fire pixels, fire bands, so F1 and F2, for the active fire detection. However, cloud masking is very, very important part of active fire detection. And for that, we will be using the band 2, 3, and 9, which are shown here in blue. Okay. So now we can actually start the exercise. Sorry about that. So I'll go back to the RUS web page and open my virtual machine. So I can use this access my virtual machine button here. Then you have to log in again to the virtual machine, so the login details are different from the login details to the portal. And this is how the virtual machine looks. So basically said, it's a remote desktop that you can, it's a Linux-based machine, so you can work on it the same way you would work on your local laptop. And you can see all the software installed here on the desktop. So we will be using Snap. For those of you who are not familiar with it, I will say a few words about it first. However, since it takes a little while to load all the products into Snap, even on a machine as strong as this, I have already preloaded all the processing steps and original data. So this is the view of Snap. Let me increase the size of the screen. And here, in this tab, it's called Product Explorer, and here you have all the loaded products that you produce or you load into your processing. Here you have some other tabs which are called Navigation and Map View. So navigation shows you, this is the view window, and navigation shows you where in the view window you are on the full scale of the product. And then you have World Map, which shows you where in the world or where on the map your products are located with the full extent of the products. So that's just for the short introduction. The Snap software is developed by ESA specifically for processing Sentinel data. So that is why we use it. And the first two products that I have loaded here are the original downloaded Sentinel-3 products. And you can see that one of them, so here's this number, and this number signifies when this product was acquired. So it's from this 18th of June 2017. And this one has been acquired at approximately 11 o'clock in the morning, or 10:54 in the morning. And the other one, so the next one, you can see that when I click this red window changes here. And the other product has been acquired on the same day at 10 o'clock in the evening. So that is Why? When I open them in RGB view, so the first product is the first view here, open in RGB, and the second product is the same RGB composition, so radiance bands during the night. So it's at 10 o'clock in the evening. So you can see that you cannot see anything on that image, although it covers exactly the same area in the view here. So I will explain a little bit how we can use the night products in actually deriving the active fire pixels. We will go through all the processing, so you will see that even the night pixels or not night acquisitions can give us very good information. So first what we need to do is pre-processing on both of our products. So the processing or pre-processing and processing of the day and night products differs slightly. So I will first go through all the steps that we need to do to pre-process the day product, so the product number 1 here acquired at 10 o'clock in the morning. And then I will explain everything about the night product. So all of these here are already my pre-processed data in order not to have to process during the webinar. However, if you start by yourself, you will probably just have these 2, and then you will go through each of these steps. For the day pre-processing or day image pre-processing. So first thing, or the most important thing that we need to do in order to be able to detect active fire pixels, we need to perform cloud masking. It is essential to detection of active fires because optically thick clouds will make the detection of active fire pixels impossible if we use passive remote sensing. Moreover, the solar reflected medium infrared radiation from certain clouds can appear similar to the fire signals, and some cloud-contaminated pixels will likely be falsely classified as fires if they're not masked out prior to the detection. So this product that we have here, as I mentioned, is a level 1B product, contains cloud mask. It actually contains multiple cloud masks and then a combination of those. However, some cloud mask algorithms, such as the ones used for this product, also identify optically thick smoke as cloud, even though fire detection can typically be made through smoke, as smoke is generally relatively transparent at medium wave infrared wavelengths, unlike meteorological cloud. So this makes the cloud masks available in the product unsuitable for the fire detection that we want to perform. And we have to derive our own mask. I will mention a little bit more about the cloud mask a little bit later when we are actually deriving it. But prior to that, we need to convert the radiance values to reflectance. And this is precisely due to the fact that we need to use the reflectance values to derive the mask. And the mask that we are using uses reflectance and not radiance. So this is the first step that we have to perform. And we can do this by selecting the first product, so the one that we wish to process, then going to optical, pre-processing, and radiance to reflectance processor. And this processor enables us to convert all the radiance values to reflectance. Let me increase the size of the window a little bit. So first, we have to make sure that in the source product we have the first product that is loaded, so the day product. Then we can change the name of the product to make it a little bit more short, because the Sentinel-3 product names are generally very, very long. For example, like this, and then we have to choose the location where to save our processing results. So there we go. And then we have to set the processing parameters. So here you can choose the sensor that you have, that your data are, in order for the processor to know what data it is processing. So here we need to select the SLSTR 500. Why only 500? So as I mentioned, the radiance bands are at the resolution of 500 meters. There is also 1,000 meters resolution bands. However, those are not given in radians, those are given in brightness temperatures. I will explain a little bit later what brightness temperatures actually are. Then here we need to check the conversion mode, so we want to convert radiance to reflectance. You also can convert backwards. And we also want to choose or select all the 3 options here. So we want to copy the tie point grids, flag and mask bands, and non-spectral bands, just in order to keep the whole product together. And then we can click run. This takes approximately half a minute, but since that would delay our webinar, I will not actually run the processing as I have the result already preloaded. So I will not click run, I will just click close and show you the product. So once the processing would have finished, it would be automatically loaded into Snap, and it would appear as number 3 as I have it here. So we can now see that all the bands here, so generally what I haven't said before is that the Sentinel-3 SLSTR products are quite complex. However, once you start to understand the structure, it becomes less complicated. So we can see the fire bands here, fire bands in brightness temperature, in a nadir view. Here is the same but in oblique view, so that's the O at the end. Then we have the brightness temperatures that are not optimized for fire detection, so that's here, bands 7 to 9. And then we have the bands here are the reflectances that have, sorry, that's the exception, reflectances here. So that's the reflectance bands that have previously been radiance bands, and they are now converted to the reflectance. And that's basically all the bands that we will be needing for this exercise. So for the next step, the image that we just derived will look exactly the same as the view that we have here, so there's no need to open it, and I can just proceed with the processing. So the next step in the processing is resampling. So again, I've mentioned this several times, there's bands with different pixel size, 500 and 1000 meters present in the product, and Snap generally has problems working with products that have multiple different sizes of the bands or pixels. So what we need to do is we need to resample all the bands that we want to use into a single resolution. For us it's going to be 1 kilometer resolution, since most important part is the fire bands, and those are by default 1 kilometer resolution, and resampling them to 500 will not actually provide us with any more information. So how do we do this? So we select the radiance to reflectance converted product, and we go to raster, geometric operations, resampling. Okay, and here we need to make sure that in the EO parameters tab, we select the radiance to reflectance product, so product number 3. We don't actually need to change the name anymore, because every operator that we use will append a suffix to the product name, or the input product name. In this case, we can also select that we do not wish to save the product physically, which saves this space, since we don't really need the product to be saved physically as we are continuing to process it. So once we would close Snap, the product would disappear, but however, for this purpose we can leave it as it is, but it's something to bear in mind. So, and in the resampling parameters, we can set, we have 3 options how to define the size of the resampled product. So we can use a reference band from the source product, we can use, we can resample the target by height, or we can resample by pixel resolution. So we will use the reference band from source product, and we will use the fire nadir band to resample all the other bands by. So it is a little bit lower, so that would be the F1BTIN. So I select this product here, and I do not need to select any further settings. So upsampling method, downsampling method is the first, and so on. So again, I would click on run. However, I again have the product pre-processed in order not to delay. And so I will just click close and pretend that my processing has finished. And the product number 4 has appeared in the Product Explorer. Again, visually we don't really, we will not really see any change, or not much of it, at least. So we will not open the product, but we will proceed with the processing. So what we need to do next is to reproject the product. So Sentinel-3 level 1B products are geolocated, but they are not projected. Therefore, in this step, we will reproject the data into non-geographic projection. And we can do this by going to raster, geometric operations, reprojections. So again, we need to be careful to have the correct product selected. Generally, it's best to select it prior to opening the operator in your Product Explorer, and then it's automatically loaded here. We see that this time the default setting is to save the product. However, we can, of course, deselect it. I will leave it as it is. And in the next step, we can choose the projection parameters. So we will reproject into UTM projection based on the WGS datum. So that's here. No, sorry, that's automatic. If you choose the automatic, it will derive the zone. However, for product that is of this size, it's generally better to find out which zone you want to use and then select it and select it here. So I go to projection parameters and I select zone 29, which corresponds to this part of Portugal. Perfect. Again, I do not need to set anything else, and I can just click run. The same as with the previous ones, I will not actually run the tool, so I will close the processing. And this is my result here. And the last step we need to apply in order to preprocess our data is a subset. Since the product is very large, let me show you just exactly how large it is. So if I close the night product, this is the full extent. And you can actually see here in this area, this is where the area of the fire is actually visible even from on this image. So this is the area of interest. So we actually want to subset the product in order to make the processing time smaller or shorter, sorry. So to subset, we can use again the tool available in Snap. So we go to raster, subset, and we get this view where we can subset using several different options. So we can either subset by dragging this blue rectangle. I don't know how visible it is on your screens, but we can drag this blue rectangle to define the area of subset. However, you can see that this thumbnail that's visible here actually doesn't give us much information, so that's not really the best way to do it. In this case, we can also subset using the pixel coordinates of the product, which is very nice tool in case you're processing on a single product and you don't actually need to have the same subset from multiple different products, because the pixel coordinates will not be the same for multiple products unless you're processing Sentinel-2, which is resampled to identical grid. However, for us with Sentinel-3 that's not true. And we also will need to have the same subset for both the day and the night product. So we actually would like to use the geo coordinates, which are of course same for all the products. And we can use so we have basically upper left and lower right corner of our product. So I will just fill in the details, which will be -10. And you can see that every time I input a number, this blue rectangle here changes, and it actually shows me the extent of my subset on top of the thumbnail. So you can see that compared to the full product, I really select only quite small area that I want to concentrate on. You can also use this button, which is a preview, which means that you can use the big view here to zoom in to wherever your desired subset is, and then use the preview to define this subset. But again, that only usually works if you have only one product and not multiple that you're trying to achieve to have the same subset. Okay, so I could click OK, but then again I have the subset created. Be careful because this tool in Snap does not actually physically create the product, so it doesn't write it. Again, the product is only virtual. So in this case, you cannot actually select for it to be saved. So you have to create it virtual, and then you have to go here and save the product. But again, I will just click cancel. So if now this was my subset product, I would have to right click it and go to save product as and save it to my processing location. Okay, so now let's have actually look on our final pre-processed product. So this is all the steps that we will do during the pre-processing. So I can open an RGB view by right-clicking the product and going to Open RGB Image window. And now I have the reflectance bands here. Generally, if you're opening original product, there will be a preloaded, or you will have several options of pre-specified or pre-loaded profiles or combinations of bands. However, since we renamed the bands from radiance to reflectance, Snap no longer recognizes them, so we actually need to set them ourselves. So let's just set band 3 as red, band 2 as green, we can leave, and band 1 as blue. This is not actually a true color composite, of course, because it only band 1 is actually corresponding to an optical part of the spectrum or visible part of the spectrum, which is the red color, and the band 2 and 3 actually correspond to near infrared. So we have to wait a little bit for the view to be created. There we go. So we can see that the view like this is much more readable, and we can also see here. So this is the part where the active fires are most likely to be. Of course, there can be small active fires of the size or that only take 1 pixel, but this is the major event that we are interested in. We can also see there is quite a lot of cloudiness around, but no clouds in the surroundings of our study site or of our site of interest. You can also see quite a lot of cloud. So if we have used the cloud mask available in the product, all of this area would have been masked, which in this case would not maybe mask the active fires so much. However, in case that the wind is blowing in a different direction, it might happen that your smoke is covering the active fire pixels and they are masked out. Okay, so I'm still talking about clouds, but we actually have not derived the cloud mask yet. So that is the next step that we need to perform now. Let me go back to the presentation and just show you a quick slide on the topic. There we go. So there was a simple cloud test developed for daytime and nighttime fire detection. So on this slide I'm only showing you the daytime detection. The nighttime detection is quite more simple. It was developed by Giulio in 2003. And it was developed for the ATSR sensor on board of Envisat that was for years used for active fire detection, and the SLSPR and in general Sentinel-3 is a heritage mission for Envisat. Okay, so here we use basically an algorithm or a band combination and threshold to discriminate between the cloud and no cloud pixels, and we are using the reflectance band at 0.65 micrometers of wavelength and the reflectance band at 86 or 0.86 micrometers, and we are applying 2 different thresholds to it. So we have 2 major clauses here, 1 and the second. And if the pixel corresponds or is positive in either of those, we mark it as a cloud pixel. And we are also using here the thermal band at 1.2 micrometers. Sorry, I believe that this is actually, I'm sorry, this is a mistake, so it should be 12 micrometers, not 1.2. And here I can also explain what the brightness temperature is. So as I mentioned, the thermal bands and Sentinel-3 SLSPR product are given as brightness temperatures. So brightness temperature is a measurement of the reflected radiation or emitted radiation converted to a temperature that a black body would have if it was emitting the same amount of radiance as the target pixel. I hope that makes sense. So basically the brightness temperatures are given in the unit of Kelvin as a temperature of the black body. Okay, so let's go back to our processing. Here we go. And let's derive the cloud mask. So we will use bandmath to derive the cloud mask, and we can use bandmath by right-clicking the product and going to bandmath. Then here we can define the name of the product, of the band that we wish to create, which in this case is going to be cloud mask with underscore. And then we have this option to add some description, units, and so on. And we can also select whether the band is going to be physically saved in the data or just virtual expression that is saved. So I will deselect the virtual, as I want my band to be physically saved, and then I can go to edit expression, and I can create the expression or recreate the expression that you saw in the presentation. So I actually have the expression written down right here, so I can copy paste it. There we go. So it uses the band S2 reflectance and S3 reflectance, and if the combination of the two bands or addition of these two bands is larger than 0.9 or 90%, you could 90% of reflected radiation, or if the brightness temperature at band 9 is higher than, or sorry, is lower than 265 Kelvin, or again, if the combination of the two bands is smaller or larger than 0.7 and at the same time it's 9 is smaller than 285 Kelvin, then we classify as a cloud pixel. Sorry, that is a bit confusing. However, if you see it written, it gets more simple. Okay, so I see that, so Snap automatically checks my expression, and it checks whether it can reference all the bands available in, that I specified in the expression that I input. And if it can identify them in the product, then I have no errors. If I did make an error, then Snap is going to notify me here. So I click OK, and we create the band. So here we see our cloud mask. So now if I just switch, you can see that it covers quite well our cloud area. It omits the smoke covered area here. We can also see this blue and dark blue pixels. So if you look actually here, you can see that those are not here, but that's just because those are saturated pixels and are marked as no data already. So they are not even available. They are marked also as no data in our mask. Okay, so this is the cloud mask for the day product. Now, this is basically finished preprocessing for our day product. The only thing that we need to do in order to be able to in order to process further, we need to save the cloud mask band. So I said that it's physically created. However, we still need to save the product, so it includes the band. So I would just need to click here and say save product, and the band will be saved. Okay, so now the second product is the night product. And I mentioned that the processing is slightly different, and that is mostly due to the fact that for the night product, we don't need to perform the radiance conversion, because the radiance bands don't actually carry any information that is of any use to us. So we use now the radiance bands for the cloud mask. However, for the night product, the cloud mask algorithm is not using the radiance bands because we couldn't use them, we couldn't see anything. So we use a single clause for the cloud mask band, which is using only the band, thermal band at 12 micrometers resolution. And so the preprocessing is including exactly the same steps without the radiance to reflectance conversion. So we resample, we preproject, and we subset, and then we create a cloud mask band. So again, I will create the cloud mask band really quickly. So our last finished night product is the one number 9. So I just select it and write cloud mask, deselect virtual. And I use edit expression to copy paste my cloud mask expression. So you can see here I only use the band S9, so the brightness temperature S9, and I set the threshold for clouds is that they are going to be classified as cloud if the temperature is lower or brightness temperature is lower than 265 Kelvin. Okay. So we have to wait a second before the band opens in view. There we go. So now we have, this is our cloud mask for the night product. So you can see that even though we cannot use the radiance bands, we can quite confidently use the thermal bands to discriminate clouds and later also the active fire pixels. Okay. So this is all the preprocessing that we need to do in order to process our data further. And now we can actually move to the active fire detection. So in order to make the processing more faster, I will just close and reopen the Snap completely clean. Since these products generally are stay loaded in Snap as long as it is open, and it could create some delays for us. So I will just close, I don't wish to save, and reopen Snap. Okay, and then we can go and open our preprocessed products. Okay, so just to check that all my preprocessed bands are present. So the calculated band cloud mask has been successfully saved in the night product, and also in the day product. So generally the band that you create is always appended last to the band list. Okay, and now we can actually move to active fire detection. So let's mention a little bit about it. I will go back to the presentation. Okay, so in this step we will apply a simple algorithm to detect or identify pixels containing one or more active fires at the time of the satellite overpass. So of course usually the active fire is not the same, it does not have the same extent as the 1 by 1 kilometer pixel. However, even a sub-pixel hotspot can significantly influence the response of the pixel. And this approach exploits the different responses of the middle infrared, or approximately around 4 micrometers, and the thermal infrared, approximately around 11 micrometers in wavelength, to hot subpixel targets. So we can actually see this on the graph here. So this blue line represents the ambient temperature of Earth, which is approximately around 300 Kelvin. And then the other ones represent the possible range of vegetation fire temperatures, subpixel vegetation fire temperatures. So we can see that there is quite a significant change or decrease in the spectral radiance between the band at 4 micrometers of wavelength and 11 micrometers of wavelength. So in this case, this would be our fire band 1 and fire band 2. So we can go back to the exercise, and we can actually proceed with the detection. So first thing that I'm also using, another thing that I'm also using in the detection is land cover. So in general, we would like to avoid, or we would like to only detect pixels that correspond to active fires or active forest fires. And since other surfaces, such as some urban surfaces, can actually give us false positive detections. We want to limit our detection only to pixels that are classified as land cover, forest, grassland, or other natural land covers. So in order to do this, SNAP has a very useful tool, which if you right-click, you can go to Add Land Cover Band, and then you can have a selection of multiple different land covers, and we will be using the CCI land cover from 2015. So I will do this for both of the products. And this means that automatically a land cover band is added here at the bottom. So now what I would like to do is I would like to open all the bands that I will be using for the fire detection. So that will be specifying or that I will be using in the expression or algorithm that I will be using for the active fire detection. So those will be the fire bands of FBT in Nether View 1 and 2. So I will open those in view for the daytime event. There we go. And I will also be using the cloud mask to eliminate the cloud pixels, and I will be using also the land cover that I just created. So once the land cover band opens, I can show you all the bands next to one another, so I can use the toggle horizontally. And this is all of our input bands. So if you can see this well, you can see that the hot spot or the fire event is seen very bright as opposed to the surrounding area in both. So this is the medium infrared, medium wave infrared part of the spectrum, so approximately 4 micrometers of wavelength. And this one is the thermal band at approximately 11 micrometers. Then we have the cloud mask and we have the land cover. And if we look at the classes of the land cover, I will go back to the presentation as this might be better visible. So this is the classes available in the land cover product of CCI land cover product. And we will be using all the tree cover classes, so forest classes, and shrubland, mosaic herbaceous cover, shrubland, evergreen, and grassland. So all the classes with numbers between 50 and 130. So this is the active fire detection algorithm, and it basically uses 4 different conditions. So first we have the initial test, which looks at the medium wave infrared band at 4 micrometers and thresholds the band. Afterwards, we want to eliminate the warm background, for which we use the difference between the response of the pixel at 4 micrometers and 11 micrometers. And then we use the cloud mask to eliminate the cloud pixels, and then we use the land cover to eliminate any potential pixels outside of the land covers that we want to use. So the land cover part you can use or you don't have to, obviously. It's up to you, our decision. So we know that the area that we are looking at is mostly forest cover, and in this case we can use it to eliminate false alarms. So the night algorithm is slightly different. So due to the fact that the nighttime conditions, so the cloud mask conditions and the land cover conditions will remain the same, but we need to lower our thresholds due to the cooler background response during the night, since we might end up eliminating our fire pixels within the warm background or the initial test. Okay, so let's go back to the exercise. So these are our 4 input bands. And now let's have a look how we translate these 4 conditions that I was showing you into a band math expression. So I can go now to the daytime product, I can right click again, go to band math, and I can select a name of the band as cover. I will deselect virtual, and I will again use the define expression or band math expression editor. And then I have again, in order not to have to write the expression down, I have the expression defined here. Generally, the band math expression editor is very simple to, very easy to navigate. So even if you don't have the expression to copy paste, it's enough to know the conditions, and then you can use simply all the bands from the product that you are passing the expression to are available here, and you have different constants, operators, and functions, so you can build your expression here. So it seems like my expression is fine, so I can just click OK and OK, and there we go. I will just make it a little bit larger by going to Window and Tile Single and zoom to all. And now we can see that this is my fire detection. So the white pixels correspond to potential active fire pixels. If I look at the medium wave infrared band, you can see that they correspond to the fringes of this bright area or hotspot area here. We can also see that there's few other pixels visible here. This depends on, of course, further investigation, whether those correspond to misclassified pixels or actually fire events. But we can be pretty confident that the pixels around this main event most likely correspond to hotspot fire pixels. So this is our first daytime detection, and now let's see how the fire has behaved between the nighttime or until the nighttime detection, which is approximately 12 hours later. So if I now apply the adapted algorithm also to the nighttime preprocessed product, I can click OK, and then I see my results for the nighttime detection 12 hours later. Okay, so there we go. So this is the nighttime detection. So we can see that there is a significant spread of the pixels. So we can see that this is the daytime detection. This is where the active fires have been 12 hours prior, and this is the spread that occurred between the 12 hours. So, of course, this is a product that needs some further refinement and further checking, but this is how you can detect the active fires. Once you pre-process or process your data in Snap, you can also export them into GeoTIFF and import them to QGIS and so on for further processing. So I can just show you how to actually export those. So for example, if I want to export this fire band here, I can go to File, Export, GeoTIFF, and here if I use this, the full product will be exported, so with all the bands, which we don't necessarily want. So I want to go to Subset, which is available in the Export menu, and looks exactly the same as the one that we have used, but this time I don't want to subset spatially, but I actually want to do a band subset. So I select here, Select None. Then I go all the way to the bottom and I select my calculated band here. So here it notifies me that no flag bands have been selected, but I don't actually need those, so I just select No. And I can rename the product and save it as GeoTIFF. And I can do the same for the second product, and once I have those, I can just show you how the visualization in QGIS can, for example, look. So I will close my Snap and I'll go to QGIS. So here you can see the active fire pixels as they were detected during this exercise, and they are just visualized, so they were converted into shape files, which you can do quite easily in in QGIS because our rasters are binary rasters, so zeros and ones. So the pixels that have 1 are converted into a polygon, and pixels with zeros are discarded. So this is just the conversion and different visualization. So the red color corresponds to the pixels detected in the morning for the morning acquisition, and the orange pixels are the ones detected during the nighttime acquisition. We can also, so there was a webinar that some of you may remember that we did on the 5th of December last year, and we were looking at burn area mapping for the same event. So if I actually now also open the product that we've derived then, so it was burn severity map. I can open it below my current detection. So okay, the visualization is not perfect. You can't really see it so well. But you can see that basically our fire pixels correspond to the boundary pixels of the burn marks at this point. So probably means that the fire was coming to the close or to the end and it was being tackled already. So this is the full exercise. If you would like to repeat it, you can request a virtual machine from RUS, and you can request this specific webinar with a code to be preloaded on the virtual machine, and you will be also provided with step-by-step details, step-by-step guide that exactly details all the processing steps on all the benchmark expressions and so on. So if you are requesting the virtual machine, in the first site of the request, you have a possibility to input a code corresponding to an exercise. You can also repeat many other of our webinars. So you can also input multiple. And the code for this exercise is HAZA04. You can also follow us for any future webinars on our webpage or on our Twitter, LinkedIn, Facebook, or our YouTube page, where on the YouTube you can find all the recorded webinars. We will create a summary document of the question and answer session, and we will post it on the webpage that I was showing you before, which is the RUS training webpage where you registered for the webinar. So thank you very much for attending this webinar. I hope you've enjoyed it, and see you some other time. Thank you.